NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, folks, and thank you for joining us for tonight's edition of the Von Karman Lecture Series. My name is Mark Razzie from JPL's Public Services Office, and it is my pleasure to be your host tonight. Joining us as our co-host and questions and answers moderator is my friend and colleague, Mr. Brian White. Good evening, my friend.
Good evening. It's so great to be here tonight with all of you, and I want to remind our audience that this is your space program. We want you to be involved in these conversations. So wherever you're watching this, whatever social or wherever you are, ask questions in the chat, and our amazing social media team will compile them all together, and we'll try to ask as many as we can during our talk. If you do not see that chat box, go ahead and refresh your page, and it should be right there. Now let's get on with it. Let's have some fun.
Thank you very much, my friend. So tonight we're going to be talking about near-Earth objects. You know, those are the space rocks that are often sensationalized in the movies that cause, or at least threaten to cause, the end of Earth. Well, thankfully, the really big impacts are rather rare nowadays, but that doesn't make them any less dangerous. In fact, if you consider the population densities around the world today, it's actually imperative that we continue to study these objects. So joining us tonight to talk about this from JPL's Center for Near-Earth Object Studies is Dr. Davide Finocchia. Davide works to estimate the trajectory and potential impact hazard of asteroids and comets, and he's also a member of the OSIRIS-REx mission to asteroid Bennu and the OSIRIS-APEX mission to asteroid Apophis. Good evening, Davide. Thank you so much for joining us tonight.
Good evening, Mark. Thank you so much for having me.
So, before we jump in all the way, I guess, tell us a little bit about yourself. How did you become interested in this particular field? Pardon me.
Well, I guess one of the conventional answers is that as a kid, I dreamed to become an astronomer, work for NASA, and after all, I even went to the University of Pisa, which is the hometown of Galileo Galilei. But that was not really what happened. Actually, when I told my mom that I was going to come to work for NASA, she told me, "Oh, I hadn't seen that coming." Really, what happened to me, I was in high school in my last year. I realized I was pretty good at math, and I said, "Oh, you know what? I'm going to study math in college." And I started college, and by the third year, for the way the university system works in Italy, you have to write a thesis by the end of the bachelor's program. And so I started talking to professors to see what could be a good topic for a thesis. And I met this professor, Andrea Milani, who was applying mathematical models to describe the motion of bodies in space. And I thought, wow, this is a pretty interesting application of mathematics. I'm going to give it a try. And that's how it all started. It was pretty much a coincidence.
So why is it important for us then to kind of study these kinds of objects?
Well, there is multiple reasons. I will mention the main ones, the two main ones. The first one is a purely scientific reason. Asteroids and comets are the remnants of the process of formation of the solar system. And so really these bodies are the equivalent of archaeology that we do on Earth. Instead of digging, we go and study these bodies to better understand the origins of the solar system, how the solar system evolved over time, and how we got to the place where we are now. So that's reason number one. Reason number two is that near-Earth objects can actually come inside the inner solar system, and that means there is a potential for them to come close to the Earth. If you pull up slide number one, you can see a bunch of trajectories here, and some of them get pretty close to the orbit of the Earth. And so you have to ask the question, is there a possibility for an impact? Well, we actually know that impacts are a real thing. And if you can convince yourself if you just look at the moon. If we show slide number two, you can get a nice picture of the moon and you can see its surface. And the surface is covered by craters. Those craters are really proof that the history of the moon has been filled with impacts with other bodies. And if that is true for the moon, it's also true for the Earth. And so we know that impacts have happened in the past, they can happen in the future, but that doesn't mean we should be freaking out about it. We should better understand what the timescales are, get familiar with that. And the truth is that big impacts that could cause real damage are really rare. But let's do a run through to get some numbers going and get a better understanding. So if you go to slide 3, you can see here Mexico in the map, and there is a Chicxulub crater right off the coast of the Yucatan Peninsula. That corresponds to an impact of a 10-kilometer asteroid. That's about 6 miles. And that happened 66 million years ago. That's pretty much when dinosaurs got extinct. And actually, this asteroid impact is the leading hypothesis for the extinction of dinosaurs. So this was a big body. It caused global effects throughout the planet. But such an impact happened 66 million years ago. That's a long time ago. Okay, so these kind of big bodies don't really reach the Earth that frequently. If we go to the next slide, we have another crater. That's something that you can actually see. This is the Meteor Crater in Arizona. It's a few hours from Flagstaff, and so if you get a chance, it's well worth the trip. There is a visitor center where you can see meteorites. You can get a lot of information about this crater. You can walk around the rim. It's about 1 kilometer across. And so this is something that you can really see with your eyes. It's pretty impressive, and it corresponds to an impact for an object that was about 50 meters in size. When did that happen? That was 50,000 years ago. So that's not quite as far back as 66 million years ago, but it's still way far back in the past. And so that's not something that happens all the time. If we want to really see something that is more compatible with timescales similar to our lifetime, we can go to the next slide, slide number 5. And here you can see a video of the Chelyabinsk meteor. It was February 2013, and in Russia people seems to like having dash cams in their cars, and suddenly they caught this asteroid going through the atmosphere and producing this big blast. Pretty spectacular, maybe pretty scary. This was a 20-meter sized asteroid, and so that's as big as a very nice sized house. And that's something that happens on average every 70, 80 years, so let's call it once in a lifetime event. Well, as scary as it looks, this impact didn't kill anyone. A lot of people got hurt, about 1,000 people got hurt, but mostly because they saw the big flash, they ran to the windows to see what was going on. And then the shock wave from the blast kind of shattered the glass and people got hurt. But so this is the kind of event you can expect once in a lifetime, and it didn't kill anybody. That should make us feel good about the risk that we have from these bodies. If we go to the next one, we have something now that happens more regularly. That's next slide, thanks. That's objects of about a couple meters. They reach the Earth fairly regularly, once a year, more or less. That's the typical cadence. This was 2 meters in size. It didn't make it to the ground. These objects are so small that they just disrupt in the atmosphere. And this happened above Botswana. So these are objects that do reach the Earth, but they don't really cause any damage. So that's the kind of scenario we're dealing with. Big objects that could cause a lot of damage, extremely rare. And then you work all your way down in size until you get to meter-sized objects that get here once a year or so, but they don't really do that much damage. And if we go to the next slide, number 7, here you have a map of all the fireballs that got detected by US government sensors. You can see how they cover the Earth. But these correspond really all to small objects. The biggest one is the red circle. That's the Chelyabinsk meteor. Everything else is much smaller than that. So I guess the take-home message is these things happen, but we should not really be particularly scared about it. We might want to do something to protect ourselves against that opportunity, but we should relax and feel confident that this is not something that should keep us awake at night.
Yeah, so then, that being said, what are we doing about it?
Well, if you want to do something about it, I'm going to quote my first group supervisor at JPL. His name is Don Yeomans, and if you go to slide number 8, you can see a cover of a book that he wrote about near-Earth objects, and he said, finding them before they find us. That's really the basic thing. There is nothing you can do if there is an asteroid out there on an impact trajectory unless you know about it. So we have to discover them. And along those lines, actually, we have 2 congressional mandates from the U.S. Congress to NASA. The first one in 1998, NASA was tasked with discovering and cataloging all the near-Earth objects greater than 1 kilometer with a 90% completeness. So we have to discover at least 90% of them. And why 1 kilometer? Well, 1 kilometer is the size threshold that could really make possible damage on a global scale, so global effects. We want to avoid that first. That's really the main problem that you want to get rid of. And then there was a second mandate in 2005 that extended the search all the way to a size of 140 meters. And that size threshold comes from the fact that this is really thought to be the size of an object that could cause some regional scale damage. So once you get rid of the global effects, then you want to go at the regional level. And then at some point we're going to keep going to smaller sizes. But so that's kind of the scenario. And you know, to respond to this mandate, NASA started funding search programs. And if we go to the next slide, slide number 9, you can see two examples of search programs. On the left, you have Pan-STARRS. Pan-STARRS is a ground-based telescope in Hawaii. And this telescope just observes the night sky every single time. If there is some blip of light passing through that is bright enough to be detected, this telescope is going to take it and get it. And on the right, you can see the WISE spacecraft. That is a space-based telescope, so it's orbiting the Earth, and it's making observation, this time in the infrared, which means that instead of being sensitive to the visible light, it actually detects heat. So if there is an asteroid, it's going to detect that the asteroid is warmer than the background and detect the object. And these are just two examples. There's many more programs that NASA has funded, like LINEAR, Catalina Sky Survey, Atlas. Really, the first rule is finding them. That's what you ought to do. Get telescopes out there to discover as many objects as possible. And I would say we've been doing a pretty good job at discovering objects. If you go to slide number 10, you can see the count, the number of discoveries as a function of time. On the left side of this plot, you can see things are pretty quiet. But starting in the late 90s, which is when the first congressional mandate came out, you can see that the number of discoveries is just exploding, taking off and growing exponentially, really. And sometimes, even, you know, for myself, I started working on this in 2006. There were about 4,000 near-Earth objects back then. And now in 2022, we have more than 30,000. We just passed that threshold. So we're really discovering a lot of near-Earth objects. Here you can see also that there are 3 curves. The red one is for objects greater than 1 kilometer. That's the first congressional mandate. We need to find more than 90% of those. Well, as you can see, this curve is kind of flat by now. That means that we really almost found all of them. And actually, we estimate that we found 95% of the objects greater than 1 kilometer that could come close to the Earth. So we met that requirement from the congressional mandate. And the good news is that none of these objects has a chance of reaching the Earth over the next 100 years. So not only have we found a lot of these objects, but we can also rule out any possible impact. That's great. The orange curve corresponds to the 140 meters and greater objects, and you can see that we're discovering more and more as time passes by, but that also means that there are a lot more than we still need to find. The curve is not flat yet, and in fact we estimate we're at about 40% of that population, and so there is still some work to do in the years ahead. And then we have all the others, the smaller ones that are not maybe as scary as the bigger ones, but they're still going to be found when you observe the night sky, and we're going to keep track of those as well. And again, not only are the 1 kilometer sized objects not risky in terms of impact probability, but we usually, rank each object with a scale similar to the Richter scale that you use for earthquakes. It's called Torino scale. It's 0 for lowest impact risk and 10 for highest. Well, for all these 30,000 objects that we've discovered, the Torino scale is 0, which means lowest risk. So we're in pretty good shape.
That's good to know. So how do you actually go about studying these objects? Like, what tools do you use and stuff like that?
Well, okay, so as I said, you need telescopes to discover these objects. If you go to slide number 11, you can see what the typical situation is. A telescope is going to take images of the same area in the sky over, let's say, an hour or so. And, you're going to have the fixed stars in the background, but then you can see something that is moving. The speck of light inside the purple circle is moving compared to background stars. That means you have a moving object, something in the solar system. What is it? Well, there is 2 options really. The first one is that this is a known object. And so what you try to do is to go through the catalog of known objects and try and associate a known object with these observations. If you can, that's great. You've got new observations for a previously known object. You can improve your knowledge on its orbit and other things. So that's something you have to keep doing, keeping track of the objects you already know. But if you don't find a match, then it means that you have a new object. And that's when the story of this object begins. So the next step, once you've discovered an object, what happens? Well, let's go to the next slide. We have to convert these observations, so these measurements of the position of the object in the sky, into something more practical, an orbit, a physical position in the solar system. And so what we do really, we do some trick, some magic if you want, to figure out all the orbits that are compatible with those observations. And once we have some initial positions for these objects, we can propagate the position into the future. So once we know the position at the start time, when the observations were taken, you can project the motion of the object all the way in the future. And we usually do that for the next 100 years. And we can do that because essentially you use the laws of physics. You have the gravitational force from the sun, that from the planets, you have relativity, all these terms that you combine to come up with the most accurate model for the motion of these objects and project them into the future. But even though you have a very accurate model, there is still some uncertainty in the future position of an object. And the reason for that is that there might be many possible orbits compatible with the observational data. That's why it's so important to keep track of all these possible orbits, because maybe there is a close approach in the future, you can determine that, but you don't know exactly how close the object is going to be to the Earth. Or maybe there is even an impossible impact. Who knows, maybe one of those orbits leads to an impact with Earth. And so that's why whenever we find that, we actually post the results on our website. We produce numbers, and we say this object that has been discovered has an impact probability of, let's say, 0.1% or whatever. And that's important because astronomers know that that object deserves to be tracked. And so they point their telescope to get additional observations of that object. And when that happens, we go to the next slide, number 13. Well, you get to refine the path because, at the beginning you had, let's say, 10 possible orbits. I'm just making a number up, 10. You start with 10 possible orbits with the data. You get additional observations, and maybe 5 of those orbits are not possible anymore. You get additional observation, and you toss 3 more, and you're left with a smaller and smaller region of possible orbits, and you refine the path. And eventually you're going to be able to say, okay, this object is actually going to pass close to the Earth at this distance, at this time. And you're going to say maybe, if the object is not on an impact trajectory, you're going to say, okay, we can rule out that impact. We're good. For the next 100 years, we don't need to worry about this object. On the other hand, if the object were to be on an impact trajectory, thanks to the additional data, you can better ensure that the object is on an impact trajectory and even estimate the impact location. So it's so important to track these objects even after they're discovered. And so that's really what we do, projecting their motion into the future, see if impact is a possibility, and in that case, try and get more data to rule that out.
So then, what do we do if we do detect something actually coming this way then?
Well, if that were to happen, there's a few things you can do. So it really depends on the specific situation. If you have a small object, let's say a Chelyabinsk size object, something like that, 20 meters, it could do some damage, but it's not really gonna cause massive or global level damage. Well, in that case, maybe you want to evacuate the area that would be affected. So if you know ahead of time, you just move people out of the way, you protect your assets, you deal with local agencies on the territory and avoid the problem. If you have something bigger that could cause substantial damage, well, in that case, you really want to move it out of the way. So you really need to deflect its path so that it misses the Earth instead of hitting it. And in that case, there are a few techniques, but I'm just going to mention one. It's called the kinetic impactor technique. The idea is very simple. You send a spacecraft in space. The spacecraft is going to approach the asteroid at a very high velocity and smash into it as hard as it can. And by doing that, you're just going to perturb the velocity of the asteroid. And if you do it right, the asteroid is going to change its trajectory just by the right amount so that it misses the Earth. Why am I touching on this specific technique? Because we just had a spectacular demonstration of this technique last month. The DART mission, where DART stands for Double Asteroid Redirection Test, was actually a technology demonstration to prove that you can target and hit a body and deflect it. And so if you go to the next slide, which is number 15, you can see the final phase and a bunch of images collected by the DART mission. The DART mission was targeting a so-called binary system. So instead of having a single asteroid, you had two. The main one, called Didymos, and the moon orbiting the main one, called Dimorphos. This mission was targeting the moon, and hopefully we can see the movie again. So this mission was targeting the moon, which is about 160 meters, and it's a perfect bullseye. Hit the target right spot on. And so that was a perfect success. We can target an object of that size and hit it. And the next step has been that of measuring how much we deflected it. And that's very important because if you ever need to deflect an asteroid, you want to know how the asteroid responds to a possible impact. And the deflection on these Dimorphos secondary asteroid has been measured to be changing the orbital period around the primary by 32 minutes. And so now we have a better understanding on how the asteroid responds. And if we ever need to do that, we are actually better equipped before before this mission. The other thing I would mention is that sometimes it can be hard to relate to things happening in space. But in this case, we also got some spectacular images from the ground. If you go to the next slide, number 16, you can see a bunch of images collected by the Atlas survey. And you can see exactly when the impact happens. There is this cloud of debris, of ejecta coming off the asteroid, and it's making this, big cloud around the main body. It's just spectacular. So you could have gone to the telescope and observed this as it was happening. So to me, that's beautiful. And that's actually the image that I show to friends and families when I talk about DART. It says, you see, you could have seen that at the telescope. That's just beautiful.
Yeah, it pretty much clobbered that thing.
Yep.
So, have we ever had anything that you might consider an exceptional case?
Well, I think if you talk about exceptional asteroids, I cannot really fail to mention Apophis. Apophis has been the poster child for impact hazards since I started. Actually, I started working in the field in 2006, and Apophis was discovered in 2004, but in 2006, everybody was talking about this object. And why is that? Well, first, let's take a look at Apophis. If you go to slide 17, you can see some radar images of this object. On the right, you have the actual data, and on the left, you have some shape modeling to get a sense of really how the shape of this object looks like. This is an object of 340 meters. So that's certainly above the threshold of regional damage. It certainly could cause some substantial damage if this object were on an impact trajectory. Well, if you go to the next slide, you can see why Apophis became so popular, so to speak, within the community. Here you can see the orbit of Apophis in white and that of the Earth in blue. You can see that they intersect. Okay. In 2004, it was actually detected that Apophis was going to make a close approach to Earth in 2029. But the uncertainties at that time had allowed an Earth impact, and the impact probability was pretty substantial. It was almost 3%. Now, you might say, okay, 3%, that means there is a 97% probability that that's not going to happen, which is true. But for a risk like an asteroid impact, for an object of this size, 3% is very high. I was mentioning earlier on that Torino scale from 0 to 10. Well, Apophis ranked 4 at the time. That's something never happened again. Never before and never after this event. So Apophis was really exceptional, standing out among the other objects in terms of impact hazard. Of course, that means that astronomers started keeping track of this object. Some additional data were reported in 2004, the year of discovery. And with those detections, we were able to prove that Apophis was not going to hit in 2029. Still, there remained some additional possible impacts later in the century, and so we kept tracking Apophis all the way to 2021. That's when the last observation was taken. And with all this data, including radar data, which are really powerful to constraining an object's trajectory, we can rule out any possible impact for the next 100 years. So I think Apophis is kind of a good story. It shows what happens. You get some initial observations. You might have a possible impact. You observe the object again, improve your estimate, and rule that out. The other good aspect of this, I would say, is that if Apophis had been on an impact trajectory, we would have been warned 25 years prior. And so we would have had 25 years of time from 2004 to 2029 to deal with it. And so that's exactly what you want. If there is something out there on an impact trajectory, we need to know early so that we can act on it.
It's very comforting to know it's going to miss. I'm not going to lie. Mm-hmm. Do we know how close it's going to get, though, when it gets in the neighborhood here?
Well, yeah, so even though Apophis is going to miss in 2029, it's going to come really, really close to Earth. It's going to make a close approach at about 31,000 kilometers off the surface. That means about a tenth of a lunar distance. If you go to the next slide, you can get an animation of the close approach of Apophis. You can see coming from the right. As a comparison, you can see the geosynchronous satellites in orbit about the Earth. And so you can see how close Apophis actually gets to the Earth. It's going to be so close, actually, that you're going to be able to see it with the naked eye. Given its size, Apophis is actually going to be as bright as the stars in the Little Dipper. So if you are in the right location in the world, which really means Europe, Africa, or even better, cruise ship in the Atlantic Ocean, you're going to be able to get, you can see this object just looking at the night sky. That's incredibly cool. And the other thing I should mention is when an asteroid comes this close, a lot of things can happen to it. It's actually going to be an experiment that nature does for us. That's something that Rick Binzel, a colleague of mine, likes to say all the time. We have nature running the experiment for us. We just need to observe it. And so if you can see the object with the naked eye, you can imagine now how good of what kind of data we can get using telescopes and radar from the ground. Because Apophis might undergo a change in rotation state because of tidal forces, which are really the same forces that cause tides on Earth. So that could change the rotation state of Apophis. You can have material moving from on the surface. You can have particles getting ejected from the body. And so we're going to be ready to observe this object and see what happens. The other piece of good news, I would say, is that Apophis is actually accessible to a spacecraft. And there is already a spacecraft out there ready for it. If we go to the next slide, we can see the OSIRIS-REx spacecraft. OSIRIS-REx is a mission that launched in 2016, and it's the first US sample return mission. This mission went to asteroid Bennu, which is another near-Earth object, went down to the surface, collected a sample, and actually we can see that on the next slide. You can see the sequence when a sample from the surface of Bennu was collected. This sample is going to be brought to Earth next year to be studied. So that's going to be incredibly exciting. I don't know what we're going to learn. I want to be surprised. Let's see what this precious sample is going to teach us about this object. And OSIRIS-REx also did all sorts of other things. He learned a lot about Bennu. He measured its mass, density, mass distribution, surface properties, thermal properties, and whatever you can think of. It was a really a great mission for learning about these objects. Well, after returning the sample to Earth, the OSIRIS-REx spacecraft is going to transition into the extended phase of the mission. It's going to change name. It's going to become OSIRIS-APEX. It's going to change the trajectory and going to make an encounter with Apophis. It's going to reach Apophis after the 2029 encounter, and we're going to orbit this object and learn a lot about Apophis as well. So that's pretty exciting. Not only we get to see Apophis making the close approach and observing it from the ground, we are also going to send a spacecraft and get incredible data.
That's going to be really, really neat. Can't wait to see the close-up images of that thing. So we've all seen shooting stars before, which are, I guess, thankfully, mostly, tiny objects that burn up before they ever hit the ground. But have you ever had the opportunity to study an actual impact?
Yeah, that's happened a couple of times. I would say, I think it's 5 times we've had an object observed before making an impact. Every single time it was a small object, a few meters, so no damage on the ground. It is wrapped in the atmosphere. But they're very good dry runs for us because we get some data and we want to see whether we're able to respond to figure out what the impact location is going to be. So the last one was in March 2022, so just a few months ago. The name of the object was 2022 EB5, and that day I was not working. These things never happen at the right time. I was actually spending some quality time with my daughters, and at some point I get a text message, and that's our automatic software alerting me that there is a possible impact within 2 hours. I'm like, oh really? Only 2 hours? We really have to get going. So I rush to my computer. I start taking a look at the data, making sure that everything is correct. And in fact, we have an object headed for impact. It's very small, just a couple meters. So no need to be concerned about this one. But let's see if we can pinpoint the impact location. So we see if observers can collect more data, and sure enough, they do. We get additional data. And thanks to the additional data, we're actually able to pinpoint the impact location. Let's look at the slide 22, where we can see the actual trajectory of this object. And it's coming in from there, and it reaches the Earth above the Norwegian Sea. So that was our prediction, and later we got confirmation through infrasound data and also a fireball detection by US government sensors that confirmed the impact location. So these cases are not alarming, but they're great tests for us. The system was capable of going from first detection to impact location in less than 2 hours. which gives us good confidence that we can do that even for objects that could be more dangerous in case that is ever needed.
Yeah, that's an impressive technological feat right there. Very neat. I think at this point we should probably reach out and see how the questions are coming in. So, Brian, how's it looking out there, my friend?
Oh, so many questions, so many great questions, and so many people are so interested. Lots of so's right now. But Flap on Twitter is asking, how do we know about the density of these? You talked about the size, but do you know if they're more solid? Are they pile of rocks? Are they dust? How do we understand that?
Well, so it's not really easy to measure the mass of an object from the ground. It's been done actually for Bennu. For Bennu, we were able to detect a perturbation on its motion called Yarkovsky effect, and that perturbation actually depends on the mass of the object. And so by knowing that perturbation, we were able to figure out the mass, and that was later confirmed by the OSIRIS-REx mission. But in general, you don't really know the mass, and so what you can do is maybe get spectra on these objects and get a good sense of what the composition of these objects, what they're made of, and you can compare that to meteorites that you collected on Earth and infer what the density of those objects is.
Very cool. Bartholomew on LinkedIn is asking, do we have more discoveries now because we're paying more attention to them?
Well, I think really it's really a function of what instruments you're using for discovering, and our telescopes have gotten better over time, and they're detecting fainter and fainter objects, and so it's just a natural consequence of having better instruments.
Wonderful. This is from Matt on LinkedIn, but they're asking on behalf of their 9-year-old. So maybe you can help them out and kind of help them with a little bit of the fear that comes in this question. They would like to know, what is more dangerous when it comes to impact size? Is it ice or metal or rock? Like, what would be the thing? And then also, as you've said, how likely is something like that going to happen?
Well, okay, so metal is really it would lead to a higher density, and that means that the object has a greater mass, and so it would release more energy. So that's what you want to avoid. But most objects are stony objects, and as I said, a big impact that could cause damage is really rare. Is already rare. If we were to do nothing and not even pay attention to them, that's very unlikely to happen. But we're also paying attention and ruling out. We got 95% of the objects greater than 1 kilometer, and none of them is going to hit. So we should not really be concerned. I got an 8-year old, and when she watched one of the Ice Age movies and she saw the asteroid impact, she was like, "Oh my God, what's going to happen to us?" But no, I was able to calm her down and explain that she should not worry about it, and that's true also for other kids, not just mine.
Is there a place for people where they can go and they can find these as they're coming through, or these results, or as we've discovered
Yeah,
them?
so if you go to the CNEOS website, we have tons of information. We report all the close approaches. We report all the possible impact probabilities and all the information you want. We have a database where we show all the orbits with also orbit diagrams so that you can get a sense of where these objects are in space. So check out our website. You're going to find all the information that you can possibly want.
All right, I want to bring us back to Apophis for a second. Bard on YouTube is asking, since Apophis is going to come close to Earth with an orbit of less than a year, will perturbation change its course over 100 years?
Well, the perturbations are going to change its course. There is no question about it. But the trick is that we have those perturbations in our model, so we know exactly how those perturbations are going to affect its motion, and we account for that when we compute its trajectory in the future.
Okay, very cool. Akshay on YouTube wants to know, because you talked about discovering them and then you have to check them with previous objects that have been discovered. Mm-hmm. How do you associate a known object with this huge catalog when you've got an object moving on your telescope?
Well, essentially for each known object, you can predict the position of the object in the sky every single night. That's actually something that astronomers do every night. They say, we want to observe this object. Let's go to the JPL website. Let's get a prediction for where the object is going to be, and I'm going to target that area in the sky and get observations. So it's not really that hard. You just need to compare the position in the sky that you measured from the data with that you get from an orbital prediction. And if they match, great, you find your match. If you don't find anything, then it's a new one.
All right. On Facebook wants to know, what what is your most challenging moment in doing observations? I think that can be a general question, but then also specifically if you have one in particular that was a really challenging moment.
Let's see. So I don't do observations myself, but I can imagine sometimes you have, let's say there is an object with some impact probability and you need to observe it, but the object is faint in the sky and the region to cover, the whole uncertainty region. We call it uncertainty region, essentially the location in the sky where the object might be. If that is large, you might have to observe many fields and cover all of them, and you might get faint detections. And so convincing yourself that you find the right object could be challenging. In terms of orbital calculation, I would say that probably the most, I wouldn't say challenging, but most interesting one was Oumuamua. In 2017, we discovered a new object, and the software was complaining that it could not find an orbit bound to the solar system. And I'm like, wait a second, what's going on here? And then it turned out that this object was an interstellar object that just came inside the solar system for a while and then now is on its way out. And so at that time I found something that I was not expecting, an object coming from outside the solar system. And so it was kind of fun to deal with that unexpected circumstance.
Well, that's a great segue into this question from Artist on Twitter. They wanted to know if, by understanding the material or these trajectories, can we understand where these objects may have formed in the region of the universe?
Yeah, so there's a lot of things you can do. Like if you can get ideas on the composition, we have what we call taxonomy. By observing the spectra of these objects, we can classify them in taxonomic types. Like we can say if this object has a given taxonomy that is similar to that of asteroid Vesta. Vesta is one of the biggest asteroids in the main belt. Well, then maybe this object actually formed from Vesta as a result of a collision with another object. That's actually something that we observed on Bennu. On Bennu, there were some boulders that didn't really match the rest of the surface of Bennu. And by analyzing those boulders, they were connected back to Vesta. And so it's very possible, if not likely, that these pieces of rocks actually formed from Vesta and somehow made it all the way to Bennu.
Very cool. There have been a couple questions about this, so I'm going to combine all of your questions, folks. Sorry. But there are questions about being near-Earth objects, but as you showed in that animation, it was kind of coming by our satellites that we have out there. Is there a possibility that near-Earth objects could become into our orbiter objects?
No, so that's an orbital dynamics thing. It's like, it really, okay. So it's very unlikely. Let me put it this way. It's really unlikely, and if the relative velocity to the Earth is high enough, that's not going to happen. But we've had a couple of cases of objects that had an orbit very similar to that of the Earth, and so when they approach, the relative velocity is not that great, and at that point you can actually enter through you can get captured by the Earth if you go through the so-called Lagrangian points and maybe stay around the Earth for a while and then leave. The last one of these objects, and we've only found two so far, it's called 2020 CD3, which stayed around for a couple of years and then left. But you really need to get close with a relative velocity that is incredibly small.
All right. We've got time for two more questions. I'm so happy that we've been able to get to so many. Thank you, folks, for asking so many wonderful questions today. But Mehdi on LinkedIn asks, has the James Webb Space Telescope helped enhance or deepened our work or research yet? If it has, how so? And if it hasn't, will it down the road?
Well, so James Webb is just getting started. It's actually, we used it to observe comet Hale-Bopp. Hale-Bopp is a comet that made a very close approach to Earth in the 90s, very close for the standards of comets. And we actually used it to observe this comet. And so James Webb can be used to study solar system bodies and learn more about them. There's no question about it. And we'll try to use it as much as we can.
Okay, and the final question, I think it's a fun question. Elliot on Facebook wants to know if you, Davide, ever get to name the objects yourself.
No, you need to be the discoverer. So I don't know. I don't do the observations. I compute the trajectory, so I don't really get to ask for a name. But a colleague of mine, Fabrizio Bernardi, named an asteroid after me as a gift for my PhD graduation. So there is a pretty not particularly exciting asteroid in the main belt whose name is Farnokia.
That's the coolest thing I've heard all day. Thank you so much, folks, for asking questions. I'm going to throw it back to you, Mark.
Thanks, everybody. Those were fantastic. Brian, thank you for moderating that. So before we wrap it up, Davide, just one more question. Like, what's next?
Well, I would say it's hard to get bored when you do what I do. There is so much fun to be had, and something exciting could be happening at any time. I showed earlier how many more objects we're discovering by the day. And in the next couple of years, we're actually going to get additional search programs. The first one is the Vera Rubin Observatory, which is going to be in Chile. It's a ground-based telescope that is very powerful. It's going to get fainter than our current search programs. And so that's going to increase the number of discoveries by a factor of 10 or so. And then we also have the ENIO Surveyor mission. That would be another space-based telescope. And similar to the WISE spacecraft, it's going to observe in the infrared. And with those two programs, we really hope that we can achieve the 90% completeness that we want on the objects greater than 140 meters among the near-Earth objects. And other things, I mentioned the OSIRIS APEX mission. I'm going to be working on that mission, and so I really look forward to analyzing the data and seeing what that mission unravels. And in general, small bodies like asteroids and comets have been getting a lot of attention. A bunch of very exciting missions have been launched to study these objects, and I don't see why that should stop. So I'm really looking forward to many more missions to these objects and learn as much as possible about them, because those are really exciting and incredibly valuable from a scientific standpoint, but also from an impact hazard perspective.
Indeed. It's nice to know the future is bright as far as that all goes. Well, folks, that's all the time we have tonight. So I'd like to thank Davide, Brian, our amazing tech team, all the outreach reps, and of course, all of you for tuning in. Remember, as we mentioned earlier, this is your space program. We're grateful for your interest and participation. So please join us next month when we'll talk about the latest in exoplanet research. Until then, stay well and stay curious. Good night.